So, Google recently announced a quantum computer that they claim is septillions of times faster than any supercomputer on Earth. It's a massive claim. So, the question is, are we witnessing the dawn of a new computing era, or is this just one of the most sophisticated marketing campaigns in the history of tech? Let's break it all down.
All right, so take a look at this. In late 2024, Google showed the world this chip, and its name is Willow. Now, on the surface, it's a 105-qubit quantum processor. But believe me, the chip itself isn't even the main story here. You see, the thing that really made headlines wasn't the piece of hardware. It was the absolutely extraordinary claim that Google made about what this little chip could do. A claim so big, it honestly sounds like something straight out of science fiction. Okay, get ready for this. Google claimed that Willow solved a problem in just 5 minutes, a problem that would take the world's fastest supercomputer a septillion years. A septillion. I mean, what even is that? It's a 1 followed by 25 zeros. It's a number so outrageously large, our brains can't even really process it. Now, when you hear a number like that, you think, okay, game over. Quantum computers are here. But hold on. The real story is, well, it's a bit more complicated than that. To really understand what Google actually pulled off, we first have to talk about the single biggest problem plaguing the entire field of quantum computing.
It all comes down to the fundamental building blocks of these machines, the qubits themselves. And they have a really, really serious problem. Think about the computer or phone you're using right now. It works on classical bits, simple, reliable switches that are either on or off, a 0 or a 1. But a qubit is a whole different animal. It can be a 0, a 1, or, and this is the magic, mind-bending part, it can be both at the exact same time. This state is called superposition, and it's where all the power comes from. But it's also what makes them unbelievably, exquisitely fragile.
And that fragility has a name: quantum noise. The best analogy is to think of a qubit as a perfect, shimmering soap bubble. The slightest disturbance, a tiny vibration, a stray magnetic field, a 1-degree change in temperature, and pop. It's gone. It loses its special quantum state. These little pops are errors, and they build up and cascade, completely destroying any calculation you're trying to run. This is the monster that everyone in the field is trying to slay.
So this tells you that the real quantum race isn't just about who can build the most qubits. No, it's about who can build smarter qubits. Qubits that can actually defend themselves and fix their own mistakes.
And the leading solution for this is an incredible concept called a logical qubit. The idea is just brilliant. Instead of trusting one single, fragile physical qubit, you use a whole team of them to work together to hold just one piece of information. They're like a crew, all constantly checking on each other, and if one of them gets knocked off course by noise, the others can spot the error and correct it. And this is a little peek at what that looks like in practice. This diagram shows Google's surface code. It's basically a grid. You have data qubits, which hold the actual information, and then you have measure qubits woven in between them. Think of the measure qubits as tiny little security guards whose only job is to constantly patrol their neighbors, checking for errors. The second they spot one, the system can flag it and fix it before it ruins the whole computation. But here's the catch, the thing that has frustrated researchers for years. For the longest time, the more physical qubits you added to your team, the more noise and errors you actually created. It was like taking 1 step forward and 2 steps back. The absolute holy grail was to find a way to cross this critical threshold, a point where adding more qubits to the team actually started to reduce the overall error rate.
And ladies and gentlemen, this chart from Google's paper is the real story. Forget the septillion years for a minute. This is the scientific breakthrough. On the bottom, you have the size of the logical qubit team. On the side, you have the error rate. For years, as scientists moved to the right on this chart, making the team bigger, that line went up. More errors. But look what happened with Willow. As they made the team bigger, the error rate went down. They crossed the line. This is the breakthrough.
Okay, so if crossing that error threshold was the real scientific victory, then what about the headline-grabbing septillion-year claim? What was the actual problem that Willow was solving?
The task is called random circuit sampling. And here's the absolute key thing you have to understand about it. It is designed to be completely and totally useless. It has zero practical application. It's a synthetic test, an obstacle course that was engineered from the ground up for one purpose: to be incredibly difficult for a normal computer, but pretty straightforward for a quantum one. It's not about solving a problem, it's about stress testing the hardware.
And hey, don't just take my word for it. The experts in the field were very quick to put this into perspective. Daniel Litter at the University of Southern California called it, quote, a problem that is cherry-picked for a quantum computer to shine, and a way to look good without offering a practical solution to anything anyone really cares about.
Chris Monroe over at Duke University was even more blunt. He said the test is, quote, totally useless, and that the only point is to prove, very indirectly, that your quantum computer is plugged in. Ouch.
Probably the best analogy I've heard for this came from computer scientist Scott Aronson. He compared it to simulating a toaster. Seriously. For a supercomputer to simulate every single quantum interaction happening inside a toaster as it makes toast, well, that would be an incredibly hard problem. But the toaster itself can make toast in a few minutes, no problem. Willow proved it's a great toaster. The only issue is that the toast it makes is a string of useless random numbers.
So once we separate the genuine science from the marketing hype, what does this milestone actually mean? Just how far are we from a truly useful quantum computer? Let's be really clear, the scientific step is huge, but the engineering mountain left to climb is immense. What Google showed was error correction while the qubits were basically sitting idle. They still have to get it working while the qubits are actually performing calculations. They have to scale from 100 qubits to millions. They have to figure out how to reliably connect multiple chips together. And they have to do all of that while managing insane levels of heat, energy, and costs. The to-do list is long.
And to really understand the scale of that mountain, just look at this comparison. On the left, we have Willow's achievement, a system of about 105 physical qubits that can suppress errors. On the right, we have what's estimated to be needed for just one of the famous applications people talk about, breaking modern encryption. The estimate is around 16 million physical qubits. We are not even in the same ballpark here. We're not even in the same city. It's because of that enormous gap that most experts are telling everyone to just be patient. As Bert de Jong from Lawrence Berkeley Laboratory puts it, it is a long shot that we will see broad commercial value in the next 5 years, maybe even the next 10 years.
So here's the real takeaway. Willow is not the finish line. It is the firing of the starting pistol in a marathon. It's the first real, hard evidence that this whole strategy, this idea of building robust logical qubits out of fragile physical ones, isn't just a theory anymore. It actually works. And that is a very, very big deal.
You could argue this moment marks the end of the beginning for quantum computing, but it also gives us a clear-eyed view of the long, hard road ahead. And it leaves us with one final thought to ponder. Is this truly the dawn of a new computing era? Or did we just witness the most sophisticated Hello World program ever written?